Welcome back. So I figured for the last SkyJam, we would do something that involved another group comparison, and we'll actually interrogate some DDA data because, as Lucas mentioned, we still, as labs, generally generate a lot of DDA data, and if you want to look at it quantitatively, that's possible in Skyline, and it's sort of the one thing we haven't covered. This is the set of methods that we've said that Skyline can support, all chromatography-based quantification, SRM, we did PRM, and we've been discussing DIA, data independent swath, with Skyline, and then finally MS1 chromatogram extraction from DDA data, which is what we're going to talk about now. So our one opportunity to talk about that just a little bit. In general, I prefer to get as quickly as possible to this, hypothesis testing mode. You can do the same types of profiling experiments that Lucas described with Skyline, and so we're going to sort of start with a profiling experiment because MS1 also does profiling, and as Lucas has just been explaining, we believe that DIA swath is going to do a better job, but you can do it with MS1, and then we're going to use the group comparison framework in Skyline to get down to a hypothesis that we might test in a subsequent experiment. I'm going to skip that one. So this is, proteomics as a field still does a lot of data-dependent acquisition, and probably most people are familiar that we have MS1 scans and then selected MSMS scans. And so we can't actually get chromatogram data out of these selected scans because they're not collected in any sort of systematic way, the way we do with data-independent acquisition. So our only opportunity to get chromatography-based quantification out of this data is to, so anyway, okay, so the workflow is we do this data-dependent acquisition, and we get these MSMS scans, and then we usually send them through a spectrum matching pipeline. Skyline supports quite a lot of those. We've already talked about that, and there's even some. What was the one that came up that we supported that's not on this list? One of them came up in this course. So then you can build a spectral library out of that spectrum matching data and then do chromatogram extraction in Skyline. And so then the chromatogram extraction that gets done is from the MS1 data. So we can't extract chromatograms out of the MSMS data because they're not collected in a systematic way the way they are with DIA swath, but we can still get chromatograms out of the MS1 data, and you've seen quite a few presentations now that we believe we reduce our dynamic range. They're, for complex samples, we believe that DIA swath is better than MS1 quantification from DDA data, but for simple samples, actually, MS1 extraction works very well, and it works very well for many things, and it's the principle that a lot of software has been based around, and certainly this is what MaxQuant is doing as well, taking chromatograms out of MS1, and then using the spectrum matches. So if I selected this peak and took a spectrum from it, and then my search engine said, oh, that spectrum is this, we use those matches to qualify these peaks and give us added confidence that they are actually measuring our peptides of interest. This is what that looks like in Skyline. This is a data set where actually the three colors that you see here represent the precursor monoisotopic precursor, the M+1 and the M+2. You can see some retention time drift. So like all of the methods that you have learned so far are, and all the features and techniques in Skyline are going to apply pretty well to this data also. You get the addition of these ID spikes. So Skyline actually annotates the chromatograms now with identifications from your spectral libraries that correlate to the data you've actually imported, whereas we have been building spectral libraries from completely different data sets and then importing, importing new data sets. In this case, we're building a spectral library and then importing that same data, and that allows us to annotate the chromatograms in that data, saying, look, we had a peptide identification for this MFL SFPTTK peptide, and we had one here and we had one here, and this actually kind of highlights one of the issues with spectrum-based quantification is if we were trying to quantify based on the spectra coming out of here using an iTrack method or a TMT method, we have very little control of where these MS spectra get collected, and so the best place for us to be quantifying on is at the peak, or even taking a chromatogram area that goes across the entire set of scans. But frequently, if we get these spectra, we have no control. They can be collected right at the beginning here, or in this case on either side. So who can tell me what kind of experiment this was? What? DDA experiment. But what? But so if you look at the peak areas, what were they doing? Calibration curve, yeah. It's another we do a lot of these calibration curve experiments, and yeah, this is pretty telltale if you see every sample going up. And in this case, this is the acquired time order. So actually, this was part of the reason I developed the acquired time order. Is I got this data set and I had it logically ordered, and it was the retention times were jumping around all over, and I was like, wow, I'm really not used to seeing this much variance in the retention time. And then when I implemented acquired time order and flipped it into that, then I got this nice smooth, change in retention time. And so now you can see that it's a calibration curve collected in 3 cycles. Okay, this can be done on instruments from all of these instrument vendors. This is the workflow again that we're gonna be looking at. DDA to spectrum matching. That's all done for us. Actually, we're gonna look at a file where the spectral library has been built and the chromatogram extraction has been done. So if you want to learn more about this, I encourage you to go do the tutorial on MS1 filtering. And then finally, we can do some quantitative analysis. We could also be building IRT libraries and doing product ion targeting, DIA swath, similar to what Lukas just described. So keys to success with MS1 data that we're going to be looking at. These are just good bullet list. Make sure you have ID annotations. If you bring your DDA data into Skyline and you don't have those spikes showing IDs, it's very unlikely that you're going to get good quantitative data out of it. So diagnose with the Spectral Library Explorer, and there's even a page on Skyline that will help you to diagnose this and figure out what's going on if you don't have your IDs. And then use this. We created a wizard for importing DDA data, which is file import peptide search wizard, and you should use that. Review retention time alignment. So we're going to take a look at the Spectral Library Explorer. We're also going to take a look at the retention time alignment viewer, and then if you can get down to where you have a hypothesis, then a lot of the data processing techniques that we've been looking at of being able to look at things and improve your data quality by noticing interferences and stuff like that are going to come into play. So it's very useful to get yourself to a point where you have a hypothesis, and we're gonna start with a broad profile and try to get to a hypothesis in this tutorial. And then you really should not need to review and manually adjust very many peaks, and you can just skip this for a big broad profiling analysis. But then when you take a very close look at your data, you may still want to do less than 5% adjustment of things. And then this is the tutorial that we're not going to do here, but which is extremely helpful in sort of getting through the entire workflow. So what we're going to be looking at here is this data from the ABRF IPRG 2014 study. What they did was they took 6 proteins and gave them fake yeast accession numbers. And these are the proteins, and this is where they come from, and their molecular weight. And then they were all coded with A, B, C, D, E, and F, and given fake accession numbers, and then put into a yeast FASTA file and given out to groups that wanted to take this data set and look for. So these are going to be differentially expressed, and then everything else is a yeast background. Actually, I'll show that in the next slide. So this is was the sample prep they did. These are the proteins along the top, and then there's three different sample preps that they used. I think collected in triplicate, so we're going to have 9 runs to be looking at, and they had different femtomol levels for each protein in each sample, and you can see how they varied them here to keep the protein amount constant. And then now we can also derive from that. So we can derive from that expected fold change when we do the various comparisons. So if we compared sample 1 to sample 2, we would expect a fold change of 0.85 for protein A and 0.27 for protein B. And so I've color coded the ones gray that I think no tool in the world is gonna find something this with such a small fold change unless we had huge sample sizes. Whereas in other cases we have much more extreme fold changes, and we really should expect Skyline and other tools to be able to find those, converting that to log2 fold change, from absolute fold change to log2 fold change, and actually defining the maximum that we see for any protein. We're seeing 4 to 5 fold log fold change for these 5 proteins, and then 2 log2 fold change. So that's a 4-fold change, and 5-fold change is like 32, right? So and we have as much as 64. So this is just to give us some, as we're thinking about this experiment, what's the likelihood that we're going to find these? They're pretty big fold changes. We're not talking about, none of them are as low as 2-fold change, right? So we feel like these should be pretty well changing proteins. So these are the DDA runs we're going to be looking at. They were run through a set of search engines and then run through this tool called iProfit in the transproteomic pipeline. And these are the number of yeast proteins that were identified, including our proteins of interest. And so what we're going to be doing here is, again, we're not even going to do the Skyline import. We're going to do the group comparisons. We're going to see if we can discover some candidates to take to the next phase. And we're not actually going to do a validation experiment, but the idea is that this is maybe something like a workflow that you would take from a profiling experiment to being ready to do a validation experiment. So this is where you would create your hypothesis. And that's it. So let's, I guess I should have got you started while I was talking. Let's pull the data set for this tutorial onto everybody's computer. If you should have the Skyline flash drive, hopefully. Do people have the Skyline flash drive, and can you plug it in? So once you have the USB drive in tutorials, there is now a IPRG 2015 data set, and you want to drag that somewhere where you have access to it. I'm just going to pull mine onto the desktop, and you put yours wherever and unfortunately this is 2 gigabytes worth of data. So these data sets are big. Profiling experiments just have bigger data sets. So let's take a look at the folder while we're copying it. Maybe some of you already have everything copied. Okay, so in the folder we have a FASTA, a 6 steady proteins FASTA, and if I open that, You can see we're not going to use this in this thing, but this is just a FASTA file composed of the 6 study proteins, and I think they're actually marked with their true identities here, and this is just for reference, you know. And then we also have this IPRG FASTA file, which is the FASTA file that was given to the participants. And if we open that, you can see that it looks like we'll see in a second, that it looks like a yeast FASTA file, and somewhere embedded in here are the proteins that were hidden from the participants, that the participants were supposed to find with some workflow, some quantitative workflow. And so we're going to do that exercise together, see if we can use Skyline to find those proteins that are expected to be changing. So if you don't already have Skyline open, you can open Skyline. And then let's see how we're doing. Are there other people copying, or am I the only one copying? Okay, there are other people copying. So what we're going to do once we get these files down is we're going to, oops, that's not what I want. So we're going to open this IRPG study all sky.zip file. You can see it's over 2 gigabytes in size, and inside of it you can see that there's a spectral library, which is a spectral library built out of those search results that I showed you on the PowerPoint, where there's 9 files, 9 DDA files got searched, and then we ran them through iProfit, and then we built a spectral library out of them. You've done this already. We had PepXML and MZXML and built the spectral library, and then I went through the import peptide search wizard and imported the data, and so that's why this file, we have a .sky file and a .skid file, which is the chromatogram data file. So I'm done importing. So I'm going to go to File, Open, and on my desktop I've got IPRG, and this is the file. And there are people still copying? Yeah? What percentage? What? You're finished? Okay. So you want to get to the point where you have, this IPRG 2015 study all.sky.zip file selected. Anybody who's got it selected can go ahead and click open. I'll leave it here for the people who aren't totally with me. Still copying? Is it 50%? Over 50%? 20% left? Okay, well that's good. Okay, well, so I'm going to open this file. I'm going to assume that once you get there, you can open it too. And this will take a little while to open, even because now Skyline has to extract everything out of the zip file into a folder before we start looking at it. Yeah?
When you import the DDA search results with the wizard or whatever, in this case, specific case, makes sense to define like a background program, because you know that it's easy, but does it make any way sense? Can you use it for some way to look for interference or whatever?
A background proteome. So the question is, does it make sense to define a background proteome before you import data from a FASTA file? And yeah, I mean, I think it's always useful to have a background proteome. So yeah, that's an interesting point, though. Yeah, maybe the wizard should create one for you. But yeah, at this point, if you wanted a background proteome for this data, you would create one. Mostly background proteomes are useful for sort of directed questions like, how unique are my peptides, and adding targets, and sort of knowing things about your background proteome. In this case, we've actually, so here it is now imported. And you can see it says updating library settings, so it's kind of working through its way through loading this data. I'm set into showing totals right now for transitions, so I could go to view transitions and go back to all, so that I can see my monoisotopic, precursor, and M+1. You can see that I don't have enough screen real estate right here to actually look at all 9 samples at the same time. So maybe I will go to view, arrange graphs, grouped, and do the same 3 grouping in a row that we did before. Are people with me? No. Okay. So anyway, so all you have to do now is go to view, arrange graphs, grouped. And then you want to set things up exactly like this. They may already be like this if you were just following along in the other tutorial. So you would have 3 distribute among groups, row, and document, and then click OK. And now you would get, a little bit more screen real estate to look at. Yeah. Okay. So let's follow my own good advice of sort of doing some logical checking, or just some initial checking of the data, whether we're going to be getting good peak areas out of this. So the first thing I said is these IDs should show up. So they're showing up. That's a good thing. One simple reason why they might not show up is if you right click on the chromatogram graph and you go to peptide ID times, you could actually turn them off. So then you wouldn't have any IDs. You wouldn't see ID annotations. Oh no, I don't have ID annotations. And you can actually turn this. There's also aligned IDs. We can turn that all off, and now we have no indication that we have any IDs or ID times. And so a good place to check, first thing to check if you don't have ID times, is to go here and turn them back on. We're going to say we want to see the matching IDs, and we want to see the aligned IDs. And the aligned IDs are using retention time alignment to map IDs from other runs into IDs for, into IDs for this run. You can see that, what I'm looking at, maybe, are you guys all looking at the same? What peptide am I looking at? Okay, so I'm looking at this GGLEP peptide. That should have been what everybody got when they open up the document. If you didn't, you can go Control F and find GGLEP. And that will get you there too. And then you can see right away that in this, what I'm looking at, there's sample 3C doesn't have an ID, but it's got aligned IDs to tell it where to find the peak. We can press F11 and zoom in, and so here presumably is something fairly peak-like that we're using the aligned IDs to tell. Like we would probably have very little way of knowing that this thing represents the peptide, and Skyline maybe would end up choosing one of these other peaks. And first of all, everybody can notice that we might certainly choose this as a really nice looking peak, right? It's like -2 ppm. So without the retention time information, we see a lot more stuff in these chromatograms than we've been seeing in the SRM data or even the DIA data. And those are interferences from other peptides, and just at the MS1 level, these look easily as good as my true peak, which is identified by these IDs. So for MS1, we really need these IDs to tell us which peak is the right one. So that's why we want to check that. We want to make sure that these ID annotations show up. because if they didn't show up, then definitely, we'd be choosing this peak over to the right as our peptide. So let's go to View Spectral Libraries to take a look at the spectral library behind all this. And it asks us to, there are some modifications that aren't defined in my document that explain some of the spectra. And so you can see, for instance, that my document doesn't have, it doesn't have, carboxymethyl M. So this must be a carboxymethyl M here, because you can see that before I click yes on this thing, there are some peptide sequences where there's no peptide icon next to them, and that just means Skyline doesn't know how to decide. It wouldn't know how to create a peptide target for you because it doesn't know what that M plus 58 modification is. And so we can click yes here, and then you'll see that you get icons next to these things, and that's primarily useful for being able to click these add and add all buttons. So if we wanted to add buttons from the Spectral Library Explorer, if we wanted to be able to add peptides from the Spectral Library Explorer, it's important that Skyline understand the modifications that the search engine found. When we're looking at data with neutral losses, Skyline can't even figure out the neutral losses without so actually this maybe has a neutral loss because it says so if we hadn't clicked yes, we would look at this data and we would not be able to Skyline would not be able to annotate this Y6 minus 64 ion because it would have no idea that this looks like a methionine, an oxidized methionine, but it would have no idea that could lose 64 Daltons. So what we're really here to look at though is to look at down here. It tells us what file this spectrum was from, and it tells us the retention time this spectrum was from. And so if we have any problems with IDs, like they don't show up, or we just got a message on the support board that somebody gave us a new format that we imported in to make a spectral library, and all the retention times showed up half where they were supposed to be. So a retention time that was supposed to be at 32 would show up at 16, and that was just a bug in parsing the new format that the retention times were showing up in. So it's useful to just sort of check your retention times here, and to check to make sure that you have source files, because that's what's going to allow you to have those ID annotations. And then you could just kind of run down through here and see that different spectra are coming from different files, and the retention times are sort of jumping around within a reasonable range. So yeah, we can see this retention time is at 100, so we would hope that we have like a 120-minute gradient. Yes?
You seem to have this precursor ion there, Mark?
Yeah, and I have A ions, and I think this all comes from when Jake Jaffe was using the computer. He turned on the A ions. So there's a certain set of things that you can turn on and off, like the 1+, 2+, and the ion types. To get the precursor ion, it's not in here. You have to right-click, and then you have more things. You could even copy these and copy them to meta files and paste them into PowerPoint. But yeah, to get the precursor, you have to right-click on the graph and make sure that precursor is checked. And if I turn it off, then it goes away. So there it is. Yes?
So where are all the ID identifications coming from? Where is from stored? I mean, here it's always just... I mean, it just points to the reference spectrum, let's say, and probably the file where you got the best scoring spectrum, right?
So Bibliospec, the tool that builds these libraries, is trying to figure out what's the best representative spectrum. And it uses, the original Bibliospec paper published an algorithm for doing this, and that turned out to work really poorly for PRM data. and it would pick the spectrum that was most similar to all the other spectra. But it turns out that if you have a lot of spectra that are down in the noise, then all of a sudden noisy spectra become really good, because it says like, whoa, this matches really well to all the other ones. And so we moved to a system where we actually pick the best scoring spectra, and then if we have multiple at that scoring level, then we'll pick the one with the highest intensity. And that does a really good job in PRM data of picking the one at the apex of the peak. So that's how we've tested it. But yeah, so we are trying. This is a non-redundant look at the spectral library. In this case we have a redundant spectral library too, and we'll take a quick look at that. I just posted an issue to the Skyline issues list to improve this, to have some of the ability to look at the redundant library too, because currently this viewer only allows you to look at the non-redundant library. And somebody said, "Oh, I really want to be able to look at the redundant library." So let's go out of here. Actually, let's click this ... button next to the name of the library, and then we can just one last thing, as we can see that in fact this library was built out of, I kind of hid the fact that there were 4 different samples. So this library is built out of more data than we've actually imported into here, but you would definitely want to check to make sure that all of your files are showing up in this list. So we click OK, close the Spectral Library Explorer, and then now if we click on the library match, or we just bring the library match tab to out, hover your cursor over that tab, library match, if you still have it there. Or I guess you should have it there based on importing, because you get the layout that I had. And then I'm going to click the push pin to hold it there for a second while we look at it. So now you can see I've got this peptide, and this is showing me the same spectrum that I would see if I looked at this peptide in the spectral library. But I also get this drop down here, which shows me all of the other identifications of this peptide. So it shows me that sample 1B, 1C, 1A, 2A, 2B, 2C, 3B. But so there's 3A and 3C are missing. And there might be, and sometimes there are multiple ID. This has one ID per file, but there might be multiple IDs per file. And if I select these, you can see that that the ID in the spectrum corresponding to the thing that I'm showing. Uh-oh. Yeah, so unfortunately the redundant library is not there. Yeah, all we have is the non-redundant library. That's too bad. But I think it's probably because the redundant library is really large, and so we already had 2 gigabytes. So you can see that some people have been like, oh, am I going to lose these retention times if I don't have the non-redundant library? And the answer is no. All the retention times get stored in the non-redundant library. The only thing that you need the redundant library for is to be able to look at the spectra. Let's look at another case where we're kind of missing data in this example at F11. F11, no, why isn't my F11 working? View, auto zoom, best peak, that's the best peak zoom, okay. So now we've got this floating dot that I hope that you guys, when you're looking at PRM data and when you're looking at DIA data, you've been getting used to being able to look at the underlying spectra for these things, right? So now let's go ahead and see if we can see the underlying spectrum for this. So go ahead and click, and you'll see that it brings up the full scan view, but then it says, well, I don't have the raw file. So we did not download the raw files. And that's one of the things I was talking about with Chorus. Is the great thing about doing a data analysis with Chorus is the raw files can stay up on Chorus, and then you can query spectra from Chorus, so you don't have to actually carry them around. They were definitely too big for me to put on the flash drive and give to you. So in this case, we're just stuck without being able to look at the underlying spectra. We have sort of a reduced reduced amount of information we can look at. So let's close that.
I could edit again, right? Could add the raw files.
Yeah, if we had the raw files and I could actually point you at the raw files, they are up on Chorus. You could download them into the folder with this Sky file, and then all of a sudden you would be able to click it. So all you have to do is get the raw files back into the folder with the Sky file, and then you can look at those. Similarly, if you have the redundant library, you could put that in there too. Okay, so let's get toward wrapping things up, and we're going to do the group comparisons that will allow us to try to find the peptides that are changing. So this is just, unlike the last sky.zip file you opened where I said it was fully processed data, this is just imported data. There's no manual processing has been done here. We're just we just use actually the last thing we have to do is verify that we have reasonable retention time alignment. So go to retention times, alignment, view retention times alignment. And so this is also critical to having reasonably good high quality peak picks is this alignment. So you view the alignment. It might take a second or two to come up, but eventually you get this alignment viewer. And this aligns every run to every other run. And here you can see all the runs aligned to sample 1B. And you can see that the R correlation between the runs is extremely high. Everything is actually over 0.999. Zero outliers. When we look at this, we feel like, well, we can see some outliers, but to the extent of this extremely high correlation, that just means that there's a whole lot of peptides on this line. And in fact, we can see that there's over 10,000 points on this line, and a handful, really, maybe less than 100 out here. So they just don't count as outliers. They're not exerting enough weight on the regression. So out of this, we get a regression with a slope and intercept, and the slopes are generally extremely close to 1. And then we have some shift about 1 minute total, I think, because we go from, well, that's, not even 1 minute total. Maximum shift of 10-20 seconds. So it's pretty good data. So we should expect really high quality results out of this. We can close that down. We feel pretty confident. So let's go ahead and define our document comparisons we're going to do. So settings, document settings. And we're going to go to group comparisons, and I already have them all defined. And actually, you probably do too, because they come in with a document. So let's just go look at these group comparisons. So this is the nice thing about when you define group comparisons, you save them with the document, and then you can go, and then they're just there. You notice that there is a sample ID annotation that's come in also. We don't really have subjects. These are actually technical replicates. So we're going to compare sample type 1 to sample type 2. And so we go to edit lists and then edit that. And that says that it's going to use the control group. The annotation is going to be sample ID. The control group is 1, compare against 2. We don't have an identity annotation. We didn't actually do any other special replication besides what we have. No normalization method, and we want 99% confidence. So, and then if you look at the other ones, they're really very much the same, except that we're changing the control group and the compare against. Oh, that's peptide scope. Yeah, actually, I want peptide scope. Oh, they're all peptide scope. Yeah, so we're going to be doing peptide scope for this thing. So they're all peptide scope. So cancel out of there. Cancel out of the document settings. And so now we're going to go apply these group comparisons. So we'll go view, group comparisons, and we can bring up this 1v2. And it might take a second or so to calculate those group comparisons. And we can see of all the things that we see in our first screen, boy, the adjusted p-value is, you know, these are not actually significant p-values. We have 27,893 comparisons. You can see we're looking at the first one. And so now we want to narrow that down a little bit to the peptides that might be changing. So we're just going to click on adjusted p-value and then click filter. And we did this before. We're going to go is less than 0.05. This time we're going to be a little bit more lenient. And eventually we're going to do a we would do a validation study to check this anyway. So we're looking for all possible changes here. So we click OK. And you can see that now gives me 42 peptides that seem to be changing between sample 1 and sample 2 at an adjusted p-value less than 0.05. We could click the show graph to graph those. You know, here's we could pull off the graph so we can see things side by side. And then we could sort by fold change, and now we see, you know, here are the fold changes. Seems to be like there are a lot more peptides that are going up than going down. But okay, so we don't really need this graph. Just kind of interesting to look at. What we're going to do now is click in this peptide column and just select all of the peptides. So just select the whole column and then Control-C to copy. What? So you want to click in the sort of the upper right-hand corner of this first peptide and then just drag down to the bottom so that you have all 42 peptides. And then Control-C to copy. And then we're just going to bring up Notepad and paste into it. So now we have a copy of those 42 peptides. And then now I'm going to go back and do this again with my other group comparison. View group comparisons 1 versus 3. Oh, actually, I forgot. I'm going to go back here, and this is still my. Okay, so I did filter by the adjusted p-value. Well, we'll just keep. Yeah. Okay. So let's let's define this this new. I'm going to manage views because I already have it. I think do people, other people, when you click here, do you see significant peptides? No. Okay. So that doesn't come with the document. So I'm gonna get rid of it for me, and then we're gonna redefine it. Okay, so we can create a view that gives us these significant peptides. So we're gonna go. We've got our default. If we click Customize View, then we can see these are the values, and you can see that you have access to other values, like you can get the unadjusted p-value and confidence level and other things that are not in this showing currently. But another thing we can do is if you double click on adjusted p-value, it selects it over here, and then when you click filter, it selects it over here, and now we can define that same filter that we just sort of defined ad hoc by clicking the column header. We can define it, and so we're gonna call this view significant peptides, and we're going to add that filter on adjusted p-value to this view, so that then whenever we want to, if we want significant peptides to 0.05, we can just flip to that view. So go ahead and add adjusted p-value by clicking that add button. Select adjusted p-value and click add button, and then click is less than, and then 0.05 or 0.05 if you have a comma as a decimal separator. But so And then click OK. And so now, we still have our 42 over here. We can now go back to this other view. And if you drop the menu, hopefully. Do people have significant peptides in the menu if you drop it for here? Yeah, so then click significant peptides and that gets rid of all the work. Wow, there's only 18 there. That seems really small to me, but okay. What? Do people have 18? Okay. I don't remember one being that small, but maybe I maybe I got something wrong. We're gonna go ahead and select those 18, copy them, and paste them. And then finally, we're going to go back here and show view group comparisons 2 versus 3. And now we can select our significant peptides for that, and there are 22 in here. And we'll copy those too. We can also sort of dock these windows together if we want, so that we just put all 3 together into one panel of 3 comparisons here. And did I paste those yet? All right, anyway, so paste the last group of 22. So select those 22 and paste them into your notepad, and so now you should have all 82 peptides, and there may be some duplication in here, but we're going to go ahead and select those 82 peptides from notepad, Control C. Then now I'm going to move this off to the side here. And I can go to Edit, Refine, Accept Peptides. And we're almost done here. So Control V to accept those peptides. People with me? Yeah? No? How far back are you?
Well, my significant peptides didn't filter for significant peptides, so I still have 42 actually. So I don't know if
That's right, 42 is what you want.
right, but how did you get the 22 then?
You have to open up so you have to go to view group comparison. You have to open up all 3 group comparisons and then set their view to significant peptides, and you should get the same. So you should get one grid for each comparison that we're doing.
Yeah, because you selected just simply 1 versus 2. If you go again,
Okay, I'm gonna have to keep going now, and then we can maybe I can help you afterwards. Okay, so what? Oh, to get to accept peptides, you go to Edit, Refine, Accept Peptides. So and then paste in the set of peptides that we had collected in the notepad. As potentially so this is just going to remove everything in the document except for those peptides. And then we also want to check remove empty proteins, because otherwise we're going to end up with a whole lot of empty proteins. Because we have thousands of proteins and only 82 peptides at this point. So, and then click OK. Skyline needs to think about that for a second. But then now you should end up with all those peptides. You can see that they come from a number of proteins. How many proteins do we have left? 29, and so we were sort of expecting, you know, maybe we should only get 5, right, or 6. The experiment said that we should only have 6. So let's take a look at this first one. And actually, the first thing let's look at is if you hover over the protein, you get this drop arrow, and if you click the drop arrow, then you can see how many peptides we actually monitored for this protein. So you can see that evidence of protein change is pretty low. But, you know, so we have this one peptide. Actually, another thing that we maybe should have done earlier is to go to refine, advanced, remove all duplicate peptides. Let's see if that actually maybe the reason this is changing is because it's actually part of that one of the other proteins that we expect to be changing. So remove duplicate peptides. Does anything go away? Nothing goes away. So there's no duplicate peptides in here. So it's not, and so now let's take a look at it. And in fact, if I move this all the way over, let's see. So the change, we have some pretty big differences between, let's see, like it looks like, oh yeah, sample 3. So this looks like a pretty reasonable change if we can, let's see, order by. Can't order it. Yeah, this has happened to me before. I don't know what's going on with the ordering. But I could go to edit, manage results, and oh yeah, it's in acquired time order. It won't let me switch out of acquired time order. So, and I don't know why that is. Okay, but anyway, you can see that sample 3 is pretty high abundance in all cases. And sample 1 and 2 are different. And so, yeah, this looks like a very significant change. We can go look at these other ones. There, you know, in this case, there's really nothing that I can see that tells me that this data is at all invalid. It looks incredibly valid. All indications, there's lots of IDs. The peaks look fine. You know, they're all the I.P values are very high. So this is like, okay, well, this really looks like a differentially expressed peptide, and why does it show up? I don't know, because it's all supposed to be constant use background. If we look at the next one, this one maybe not so much. In this case, we do have 3 cases where we have very, very different peak areas, but if we use our synchronized zooming, whoa, that didn't work so well. We maybe can see that we don't, this is not really our peak of interest, but boy, I would like to, I guess I'll just look at one of them. Oh, oops. Why am I getting it? Huh. What's happened to my zooming? Oh well. There's some interference here, right? A lot of interference, and it's so. There's something here, we can't see our peak, but we see something else. Actually, maybe if we look at these other ones, no. But yeah, so there's a lot of interference, and you know, this is not really our peak that's getting measured, and so this is, you know, we can pretty easily just discount this one. There's something going on. It's not really, you know, there was some weird interference that was causing us to get the wrong. Now in this case, we have a protein where quite a few peptides were differentially abundant and some weren't. So one of the things we might do in processing this data is to just drop this thing and say, okay, well, there's evidence of 8 different peptides here changing. It's not all of them. We might actually just go check them all by bringing this drop down and then checking that box up there. And now we could do data processing of all of these and determine whether or not we really feel like all of them contain evidence of a change. So we could look more at that. Another thing we can do, so we could certainly go one by one through these cases and determine whether which ones have interference and which ones don't. The thing I'm going to do here is I'm actually going to go ahead and do refinement, edit, refine, advanced, and I'm going to say that I want a minimum peptides per protein of 2. So I'm just going to discount all these things that only have 1 peptide in terms of my analysis, my further analysis, and then you'll see that I end up with 5 proteins, which is pretty good. And those are the 5 proteins that were changing by more than 4-fold. In this case, I've processed this data before and gotten all 6 peptides. But that one that's changing by 4-fold is kind of close to the line of our ability to detect change in this big a data set, right? So now let me quickly return to I've narrowed these down. I've got this great set of candidates. Let me quickly return to my group comparison statistics and see what they look like. And you'll see that the p-values for them are just like the adjusted p-values are incredibly good. They're all really, really low. But you can't use these p-values, right? Because these adjusted p-values are based on the set of things that we found. So actually, if we go all the way back to, let's use undo. Wow. I guess, yeah, if we get rid of the accept peptides thing, so we just go all the way back, and boy, that takes a little time because you'll see, you can't see exactly the same peptides, but there's nothing with a p-value as low as that, right? So we were just seeing p-values of 0 and 0.1, and so the thing about adjusted p-values is they're dependent on the set of things that you're testing. And so you cannot report the adjusted p-values after you've already narrowed things down, because that's not the experiment you did, right? So if you had gone in and said, oh, I want to test to see whether these 5 proteins are changing, and that had been the experiment you set up to test, you could report those p-values. But if you went in and what you were testing is these 28,000 peptides, then you have different adjusted p-values. So you got to report your adjusted p-values based on what you actually were testing, and they'll change as soon as you start deleting things. So, and that's it. Ran a little late, but got started a little late. I actually think I did exactly the hour I was allotted. And now we get to break for lunch. I guess Ben will tell us when to be back here.
Yes, so let's take an hour for lunch, so let's come back at 1:50, please. We're also going to try and squeeze in a group photograph now, so if you do whatever Betty says.